Hello and welcome to this video. In this video, we're going to look at the different quantum values that different particles can have and why we need to conserve those and how we can prove that these things are conserved in different interactions. So the first thing we're going to do is make a list of some quantum values. So we know things like energy is a quantum value. We would say momentum is a quantum value because these things are conserved. Charge is another one. We'd also have baryon number. We could also have lepton number. And we can also have strangeness. And these will probably be the ones that you'll encounter the most. But I'm also going to add, I'll put this one as a star, I'm going to add spin, since we have spoken a little bit about spin in some other videos, so I just want to mention it here because it is still a quantum value that is conserved. Okay, so all of these quantum values, the main rule is all quantum values must be conserved. Must be conserved in all interactions. Okay, there is a caveat to this. So the caveat, basically meaning exception, is strangeness. And strangeness can change with a weak interaction. Okay, so strangeness is the only one that changes. Nothing else changes in any of these interactions. So we've looked at 4 particle interactions. We looked at alpha decay, beta minus decay, beta plus decay, and electron capture. We also did a separate video on annihilation and pair production. They're still interactions, and they will still have to abide by these quantum values. Okay, we can't actually change anything about these unless it's strangeness and it's a weak interaction. So how do we decide what interaction it is? Well, if you remember the fundamental forces, we had a list of them in order of strength. So if you remember, it was the strong force first, then it was the electromagnetic, then we had the weak nuclear, then we had gravity. Okay, and the key of this is just knowing what they act on. So this was acting on quarks. This acts on charged particles. This acts on everything. And this acts on mass. Okay. Now, in order to decide whether it's a weak interaction or a strong interaction or an electromagnetic interaction, you'll probably find you're never going to get a gravity interaction in particle physics, purely because it's completely negligible because your masses are so tiny. You go down in this order and check if everything in the interaction can satisfy each of these. So, for example, if we had something that all of the particles involved in the interaction, so all of the things that go into it and all of the things that come out of the interaction are all made up of quarks, then it would be a strong interaction. But if we have loads of quarks and then one of those things is a lepton, it can no longer be a strong interaction because we have leptons in there and they don't contain quarks. So then we go down to the next one and then we say, is everything in this interaction charged? And then let's say we've got everything's charged, it's electromagnetic then. Let's say we've got loads of things charged, but then we have a neutral neutrino, or we have a neutron. It can no longer be electromagnetic because we don't have charged particles, and therefore it's weak. Okay, because gravity is weaker than the weak force itself, it means that as soon as we get to the weak force, we can stop. Okay, so gravity is basically not even existent, essentially, at particle levels. Okay. So let's show how we would prove that these quantum values are conserved. So let's look at conserving quantum values. well, let's just call it values, conserving values. Okay, I'm going to take an example of an interaction. So let's take beta minus decay. Okay, just as an interaction. We know beta minus decay from what we said is a neutron goes to a proton plus an electron plus an electron neutrino. Firstly, I want to prove now that this is actually a weak interaction, because if we look at the list, we'd go strong force first. We'd notice here that the electron and the electron neutrino, there should be an anti-electron neutrino, are not made up of quarks, so it can't be a strong interaction. And the neutrino and the neutron are both neutral particles, so they're not charged, so it can't be electromagnetic, so it has to be a weak interaction. Okay. Now, let me rewrite this a little bit further over, just so I can write some stuff. So let's write this here. Okay. We need to show that things are conserved in this interaction. Okay. It's very difficult to show that energy is conserved, purely because we'd have to do loads of calculations based on energy, and we'd have to know the velocities and all the potentials, so we don't worry about that. We will worry about charge. Okay, we're also going to worry about lepton number, baryon number, and for this case, we're not going to worry about strangeness. These are usually the three that they'll make you prove are going to be true. Okay, and the way you're going to do that is essentially write out your interaction and then just label which one is which. So if you just know that this neutron has a 0 charge, then the proton has a +1 charge, the electron has a -1, and this has a 0. On this side we have an overall 0 charge, and on this side we have a 1 -1, which is 0 plus 0, so we have a neutral charge on both sides. We do the same for lepton number. A neutron is not a lepton, so it has a 0. Proton also not a lepton, so 0. This is a lepton, so it has a lepton number of +1. This is an anti-lepton, so a lepton number of -1. So on both sides, we have a lepton number of 0. Then baryon number. Remember, if it is a baryon, it has a baryon number of 1. If it's not a baryon, it has a baryon number of 0. So a neutron is a baryon, so it has a 1. Proton is a baryon, so it has a 1. And the rest of these are zeros because they're both leptons. Okay, and you can see we have a 1 and a 1 on both sides. And this is just how we're going to show that we can conserve these values. Let me now take another interaction, and let's just look at how we would use this conservation rules to try and work backwards and see what things are left over. So let's take the example of a neutral kaon decay. So we can have a K0, and that's going to decay into a pi plus, okay? And we can also say it's going to also form a mu minus, okay? And something else, okay? So some other thing x, and they might ask you to work out what is x in this interaction, okay? What must x be in order to make this work? Okay, so what we would do is we would once again look at the charge, which I'm going to call Q, the lepton number, and the baryon number. And I'm going to introduce something in a second that we'll talk about. So let's do charge first. So that means we can work out what the charge of this thing is, what the lepton number of it is, and what the baryon number of it is. And so the charge of this is 0. Charge of this is +1. This is then -1. So this, in order for things to be conserved, must also be 0. Okay, because if we know this whole side has to add up to be neutral, and +1 minus the 1 gives us the 0, this has to also be 0. Because if it was any other charge, then it would give it one side to the equation would be charged and not the other. Lepton number, K0 is going to be 0 because it's not a lepton. Neither is pi plus because these are both mesons. Mu minus is a lepton, so it's going to have a +1, And that means in order for this to be even, for this to balance on both sides, this has to be -1. So we know so far that this is a neutral anti-lepton. And so if we know it's a lepton, we know it can't be a baryon, but let's just check. So the baryon number, this is a meson, so it's not a baryon. This is also a meson. This is a lepton, and we know that's a lepton, so it has to have 0. This line looks as if it's kind of stupid that we're just putting in a bunch of zeros, but it is necessary to show that baryon number is conserved. It is 0 on both sides, even if we have no baryons. Okay, it's still acceptable. So what we know about X is neutral, and it's an anti-lepton. Okay, now this narrows it down. We know it's definitely some sort of anti-neutrino, okay, because if we think about all the leptons, we can only ever have neutral leptons that are neutrinos, because the rest of them are all charged. And so we have a lepton because it's neutral, a neutrino because it's neutral, and it has to be anti because its lepton number was -1. But is it electron neutrino, a muon neutrino, or a tau neutrino? And the way we're going to look at that, you'd probably say it's obvious because we have a mu here. This has to be a muon neutrino. But another one of these conservation laws that isn't strictly taught at A level, but I think is useful to know, is you also have to conserve lepton type or lepton flavor. Okay, let's call it flavor for now, because it's similar to quark flavor. Lepton flavor must be conserved. Okay, meaning if I have muons on this side, I have to cancel out the muons on this side as well. So X has to be an anti-muon neutrino. Okay, if this was an electron, I would have to have an anti-electron neutrino. Okay, we could also look at muon decay as another example of this. So if we take a muon, the way a muon decays is, we said that electrons are the most stable lepton, so it's going to decay into an electron, but we're also going to have to put some neutrinos on here. It's going to decay into an anti-electron neutrino and a muon neutrino. Now the way we can know this happens is because not only do we have to conserve lepton number, so if we looked at lepton number, this is 1, this is 1, and this is -1, and this is +1. So this becomes 1, this becomes 0 plus 1, so it's 1 on both sides. So we've conserved lepton number. Conserving lepton flavor means that if we have a muon over here, we have to have something of the muon flavor on the other side as well, which is why we get this muon neutrino. And because we have an electron here, we have to cancel out the electron flavor on this side, so we get 0 on this side because we know we have no electrons on this side. So this is just another example of this extra type of conservation law that we have. Okay, so this is how we're going to conserve things. We have to conserve this whole list up here, so we have to conserve all of these things. Spin we haven't really spoken about, but it's okay, we don't really need to speak about it too much. If you want to look into it, go for it, but try not to get too caught up in it because it can get a bit confusing. So we need to know these values, we need to know how to prove that things are conserved and how to use these conservation laws to find out what's left over, and we can use this kind of trick that we've got now of this lepton flavor conservation to help us along with that. Thank you for watching.